A photon is supposed to be a particle of light, but this is not a photon, and neither is a point particle like this. That's because I think the term particle of light is extremely misleading, because at least to my mind, and I think for most people, the idea of a particle is that it's small, like it's confined to a certain area, and it moves along kind of like this. But as I'll explain in this video, photons are actually huge. They're infinitely large, spread out over a huge amount of space, and they move along like this. But wait, is a photon just a wave then? What about the particleness? Well, I'll explain in this video how a wave like this can still have a discrete and particle-like property about it, which is what makes it a photon. But I'll also explain how if you measure a photon, you end up getting a discrete particle like this somewhere along here, which you may have seen in famous photos like this, where single photon dots make up the double slit pattern. This is not a contradiction in quantum mechanics. It is possible for something to be very spread out before it's measured, and then when it is measured, it collapses to a single spot. And we'll explain in this video how that happens, like mechanistically, what goes on to force the photon into a small spot when it's measured. Okay, so I wanted to explain this all to you using an experiment called the photoelectric effect, which is really important in quantum mechanics because it was the first experiment that convinced people that photons exist, that there are particles of light. The original version of the experiment is quite complicated, so I was going to show you an at-home version, which was based on a few other YouTube videos that I'd seen with, but I wanted to do it slightly differently. I was going to do it with calcium and visible light, so you could really see what was going on. At least that was the plan, but it just didn't work, and I don't know why.
Nope. I don't get it.
So instead, what I'm going to do is I'll link to some other people's videos where they do manage to get it to work at home, and then I'll explain what I should have seen when I did the experiment. This is my diagram of the experiment. I know it looks like a weird game of hangman, but this is supposed to be the calcium metal, and here in the cup is supposed to be these bits of foil. And I started off the experiment by rubbing my hair with a plastic bottle. The point of this is that when the plastic bottle rubs against my hair, it steals some of the electrons from my hair. And then when I touch that plastic bottle against the calcium, it donates some of those extra electrons to the calcium, making the calcium net negative. But because the calcium is in electrical contact with the foil, that should make the two bits of foil move apart from each other because they're both negative. At least that was what was supposed to happen.
No, nothing. Nothing. So much for that.
That was the easy part of the experiment. That was just the setup, right? I have no idea why that didn't work. I think from now on, I'm just gonna stick with theory. But anyway, let's assume that that did happen. Now, the important part of the experiment is what happens when we shine some light on the calcium. Light has energy in it, and there are electrons that are trapped inside of this calcium because they lack energy. They don't have enough energy to escape. So in theory, by shining a light on these electrons, you might be able to give them enough energy to escape. That's what the whole photoelectric experiment is about. Whether this light is going to give enough energy to these electrons to make them escape. If it does make a bunch of electrons fly away, then we'll be able to tell because now the negative charges will spread out again and they'll be basically neutralized. And so these two bits of foil can now go back to being together. So that's what we're looking for. We're looking to see, does this light let electrons escape? All right, so first up, we'll put some red light on. And red light has quite long wavelengths. But in classical electromagnetism, it doesn't matter what the wavelength of the light is, it only matters how strong it is. So we first shine this red light weakly and we see that nothing happens. The electrons stay where they are and the foil is still separated. And so then you might think, well, all we have to do is add more energy. And in classical electromagnetism, more energy just means a bigger amplitude. And so we turn up the amplitude of the light making it brighter, which means that there's much more energy in there. And so this should be enough energy to release the electron. But we find that no matter how bright you make that red light, you will not be able to release these electrons, and the foil will stay as it is. It's the same story when you instead use yellow light. You can shine the yellow light as hard as you want, but it's not going to release any of the electrons. But things change when you instead shine some green light. Now what happens is that the electrons do get freed and these bits of foil come together. And this will also happen when we use blue light, which has even shorter wavelength. So what we found is that the intensity of the light just doesn't really matter for whether the electrons will get released or not. But the wavelength does matter. As long as the wavelength is lower than some threshold wavelength, then the light will release electrons. In our case, for calcium, it turned out that calcium requires green light or light with shorter wavelength than green. And that's why I was really excited to try and use calcium for this experiment, because it's kind of cool to see it in the visible spectrum where, like, red light doesn't work, but blue light does work. Usually for the kind of metals that are used in a lot of experiments on YouTube, like the only light that does work is like ultraviolet and above. And so it's a little bit less exciting to see that, I feel like. But I mean, how exciting is it to see this like diagram of the experiment? Anyway, the point is that this result was very, very surprising when people first did it, because this is the opposite of what you would expect from classical electromagnetism. Here's what that theory would have said. Light has energy in it, and the brighter the light, the more energy it's got. And the way that energy manifests for a wave is in its amplitude. The bigger it is, the more energy it has. In fact, the amount of energy in light is proportional to the amplitude squared. So for the energy of the light, it doesn't matter at all what the wavelength is, just how big the peaks are. The wavelength just determines the color, but the amplitude is the energy. The thing light wants to do with all of that energy is donate it to a charged particle, like this electron here. When the electron is all alone, it can receive any amount of light. The more it gets, the faster it flies off. But it's a little bit more complicated when the electron is bound up in a metal. The reason the electron is trapped in the metal in the first place is because it doesn't have enough energy to fly away. For each metal, there's a fixed amount of energy that the electron would need to break free. When light shines on it, that's the electron's opportunity for escape. The electron doesn't mind what color it is. As long as there's enough energy in the light to break it out, the electron can escape. The extra energy then might just go into how fast it flies off. Only this story is what you would expect from classical electromagnetic theory, and it turns out not to be right. So for the classical wave theory of light, the intensity, which is related to the amplitude of the light, is the only thing that should matter. But the wavelength, which is related to the color, should be completely irrelevant. But that's not what we found at all. It took Einstein coming along in 1905 to come up with an explanation for this experiment, and his explanation was a bit of a compromise. So he said that waves like this still have energy that is related to their amplitude. However, it's not possible to make the wave weaker and weaker in a continuous manner like this. Instead, waves must have a minimum amount of energy. A wave with this minimum amount of energy is called a photon. But there's another rule to this. If you wanted to add energy to this light, you can't just add any amount that you want. Instead, you have to add another photon's worth of energy, which is the same amount of energy. This new wave has a bigger amplitude, and it's called a two-photon state. So to generalize, any wave of a single color of light must be made out of a whole number of photons. Which is all very interesting, but what has this all got to do with the photoelectric effect and color and all of that? Well, the size of this minimum amount of energy, in other words, the energy of a photon, depends on the color. So if I have some light that has double the wavelength, then it has half as much energy inside of each of its photons. So here's a question for you. If I had these two bits of light then, and both of them actually had the same intensity, then what would that tell you about the number of photons inside? Well, if this light has, let's say, 2 photons worth of energy in it, and this light has the same amplitude as this one, it must have the same energy. But because each of the photons have half as much energy in this case, there must be twice as many photons to make up for the difference. So in total, the energy is related to the amplitude, but the photons are just about how you're allowed to chop up that energy. The really crucial thing for the photoelectric effect is that the longer the wavelength, the smaller the amount of energy per photon. Now, the actual equation doesn't really matter too much, but just knowing this will be enough to understand the photoelectric effect. When light interacts with an electron, instead of giving that electron all of the energy, it gives the electron just one photon's worth. We'll get back to why in a moment because that is super important, but for now let's just go along with it. So let's say we have a color of light that has really big photons. And so if that one photon has enough energy to free the electron will take that freedom plus any surplus energy will just go into its kinetic energy. On the other hand, we might have another color of light shining with a lot less energy per photon. Now the electron won't get enough energy to escape from one photon. So it doesn't take any energy at all. Even though many photons may be raining down on it, none of them are good enough. So it's the fact that energy is broken up into chunks like this and that electrons can only take one chunk at a time that explains the photoelectric effect. But what does this tell us about photons? Like, what are photons? Well, we can now see what's sort of discrete and particle-like about these photons. The amount of energy is discretized, and so we can talk about like a number of photons inside of the light, which feels very particle-like. But on the other hand, they're not particle-like in that it's nothing to do with how spread out they are in space. Now, I know that doesn't sound very satisfying because I think the word particle very much evokes something that is confined in space, which is why I think this picture of a photon has become very popular. Honestly, I used to think that photons look like this. I mean, it's so tempting, right? It's still a wave, it's still wavy, but it's confined to a certain space. It just seems like this is what a photon should be. It's so tempting to think of something like this as a photon, rather than an infinite wave like this. I mean, this moving along like that looks way more particle-like than this moving like this. And plus, you've probably seen those experiments where when you measure where a photon is, it turns up as a little dot like this. Doesn't that prove that a photon must be small? Well, not quite, and it's because quantum measurements are really weird. Remember that we can only talk about the energy of a photon when it has a well-defined wavelength. On the other hand, most light doesn't have a well-defined wavelength. In fact, it's a mixture of many different colors. For example, purple RGB light is actually just made out of red light plus blue light. When you add different lights together, you get weird-looking waves. Here you can still talk about photons, but you'd need to say that there are this many blue photons and this many red photons. This kind of wave is a real type of wave and they're very useful. It's called a Gaussian wave packet, and it's not made out of a single color of light. Instead, it's made out of one main color, like this one, and then a bunch of other colors that are nearby to the main color. So for example, this one that's slightly longer. When you add enough of these different colors of light together, you get something that looks like the Gaussian wave packet. And that's why this is not a single photon. This is a mix of different colors, which means it's a mix of different photons. A single photon state must be a pure color state like this one. You can see that this type of light needs to be spread out infinitely long all across the universe, which is why this kind of light, photons, they're a fiction. They don't really exist. But sometimes we can kind of approximate a photon by having a single laser, let's say, of light that's across a very big space, like, in the double slit experiment. So it's approximately an n photon state, or a plane wave, as we like to call them, but you never actually have real photons in real life. Okay, but now for the really interesting question. Why is it that when you measure a photon, it goes from being this infinitely big thing to just a single dot in a random spot? This is something it took me a really long time to get my head around, But it was thinking about the photoelectric effect experiment that finally made me feel like I understood the answer to this question. So let's go back to the experiment, or rather my cartoon version of the experiment. So one very typical way to measure a single photon of light is to use something called a single photon avalanche detector, and it's actually based on the photoelectric effect. So imagine this is our calcium metal from earlier, and we're going to shine some light on it in this whole area, right? And let's say that there's only 1 photon worth of light coming out of here every second. So what's going to happen? Well, what might happen is that a single electron from this calcium gets ejected. And if we're super, super clever about it, it is possible to amplify up this tiny, tiny little current to an amount that's actually measurable. And so you can measure that this electron got ejected from this calcium. But now you've learned something else as well. This photon of light that was spread all across this entire area has now been measured just inside of this confined of this calcium. In other words, you've done an approximate position measurement of this photon and you found that it was inside of here and not out here somewhere. If you make the metal even smaller and you measure an electron being ejected, now you've done an even more precise position measurement of the photon. Now suppose you made an entire grid of these little metals and you make that grid big enough to cover the entire area that this 1 photon will shine on. What's going to happen? Well, the photon is going to turn up in just one of those spots, randomly. This is how you get photos of single photons. It's actually a pixel array of these little photoelectric effect experiments going on. And when the photon hits one of these, then the current is detected in that pixel and that pixel's colored in. But this is weird, right? If the photon shines on the entire grid, then why don't we get a sort of mini current in every single one of these rather than a big current in just one of them? That's exactly what would happen if the electrons acted in a classical way and they were able to accept any amount of energy. But remember, the electrons don't act that way. In fact, these electrons will only accept enough energy to let them escape from the metal. Otherwise, they won't take any energy. And when you shine this light at the grid, each one of the grid points is not getting enough energy to release the electron. But the way that quantum mechanics deals with this is it says that instead of all of these pixels getting a small amount of energy, one of them randomly will get the entire photon worth. And that's where the electron will be ejected, and that's where you'll measure a current. It is unsettling that the result of this measurement is random. Like if you did this experiment again, maybe the photon will turn up here this time, and maybe next time it will turn up here. This does explain why the electrons only take 1 photon worth of energy at a time though. Say there are many photons worth of energy shone on this area in a short period of time. Because it's random where those photons will show up and be absorbed, as well as when those absorptions will happen, it's very unlikely that a single electron will absorb 2 photons before it escapes. This also explains something that I was very confused about even after I finished shooting this video. I thought that the amplitudes of these waves had to be discrete, but that's actually wrong. They can be any value at all. And the reason is because the amplitude is related to the power, in other words, the energy per second. This makes sense because if you had a light on for a longer amount of time, then you'd be using more energy than if you had it on for a short amount of time. But let's say you measure how long it takes for a photon worth of energy to be absorbed from a bit of light. If you have a big wave with high power, then it'll be a short time before the first photon of energy arrives. On the other hand, if you have a small wave with low power, then that means it'll take longer before you absorb the first photon worth of energy. But you can see how any amplitude is then allowed, because a smaller amplitude just means that you have to wait longer for the photon to arrive. But the thing that's discrete is just the amount of energy in each of those photons, and not the power itself. But a consequence of that is that it's wrong to call a wave like this a photon. Even if we make the amplitude really, really small, that just increases the time it takes for a photon to arrive. But if you keep that light on forever, which you have to for a plane wave, then photons will keep arriving very slowly forever. And so the only way to get a true one photon state is to decrease the amplitude to almost zero, but not actually zero, so that it takes an infinite amount of time before a photon of light will arrive. That's obviously fictional, but it's a very convenient fiction when you're working in theory. In practice, though, when people say that they've done an experiment with one photon at a time, like for example with the double slit experiment, what they actually mean is that there was only one photon worth of energy per a short unit of time. And I feel like the results of those single photon at a time experiments are only really surprising if you believe that photons look like this. But photon states are actually just waves that spread out and go through both slits, and so of course there's still an interference pattern. Huygens Optics does a really great video where he does one of these experiments and explains exactly what's going on, so I highly recommend that. But let's go back to the main video now, because there's one last thing that I found really surprising that I want to tell you about photons. Originally, if the photon was spread out like this and had a single color of light, but when you measure it, it ends up becoming confined and could end up in a state more like this Gaussian wave packet. Doesn't that mean that it's changed color? Like, remember we said that the Gaussian wave packet mainly was this color, but has other colors in it. And so if you did a position measurement of light and at the same time an energy measurement, so you can do an approximate energy measurement, which will tell you the approximate color, then doesn't that mean that you'll sometimes measure a single color of light to suddenly have different colors inside of it? Well, I thought that was just too weird to be true, and so that had made me a bit doubtful about this entire picture. But then recently I heard about an experiment that a group had done that very cleverly confines a laser light to a very, very small amount of space. And this is the result they found. They found that there is a probability of getting different colors of light. Honestly, quantum mechanics is so weird, and I feel like I'm still learning so much about it. I started on this video series having almost no idea what light was, even though I'd taken plenty of classes on it. And doing these experiments pretty much changed my mind on the little I thought I did know, like that light is fundamentally a particle. It took a while, and there's still lots that I don't know, but this is my understanding of light now. Light is a wave of the electromagnetic field, but what's particle-like about it is that it only delivers discrete packets of energy when it interacts with matter. If you'd like to see the full journey I took to get to this conclusion, here's a link to the series. Thank you Screen Australia and YouTube for supporting these videos. It's been so much fun.